Okay, so let's have a look at the graphs of e to the power of x and e to the power of minus x. So we're going to quickly just draw up a table of values for these, because what we'll notice is something really cool that happens between these two. Okay, so what we're going to do is we're just going to substitute our values for e to the x and e to the minus x, and we'll start from minus 2. We'll go down to up to 2, and the same for this one too. So we discovered in the previous few chapters that e to the x and e to the minus x are just reflections of each other in the y-axis. Okay, so, or in the x-axis. I can't remember. We'll have a look in a moment anyway, and we'll be able to see it. So essentially what we've got here is we've got two table values. So let's fill these out. So we've got e to the power of negative 2x. Well, that's the same as 1 over e squared. E to the power of negative 1 is 1 over e. E to the power of 0 is 1, and an e squared. If we do this with e to the negative x, what happens is we get the same thing, but we get this reflection. Now, what you'll notice is we've got 2 points where the values are the same. So if we have a look at the graphs of these two, so if we have a look at y is equal to f of x is equal to e of x, and let's actually go back to where we are, and we'll type in our other function, is e to the negative x. Okay, so it's in the y-axis, not the x-axis. So what you'll notice is we have these 2 points here. Okay, now if we were to draw the tangents of these 2 points, okay, so if we had the tangents of these 2 points here, they're both at 0, 1. So if we were to find the derivative at that point of intersection of both of the sides, so if y is equal to e to the x, then dy dx is equal to e to the 0, which is equal to e to the x, and on this side we've got y is equal to e to the negative x, so dy dx is equal to negative e to the negative x. Okay, if we substitute that 0 value into both of these, so at x is equal to 0, at x is equal to 0, what we get is you get the derivative value being equal to 1 and negative 1, which means that the gradients are perpendicular to each other. So that means that that those two gradients, the tangents at the point 0, 1, would be perpendicular to each other, which is just a really cool fact about these exponential functions. So what we're going to do is we're going to have a look at how we can use some integration and some differentiation and some calculus, and to find the tangents and normals of these curves. So we have got differentiate y is equal to x minus e to the x, and then what values of x is the curve stationary. Well, this is a nice straightforward differentiation question because it's a linear factor of functions, so we can just break this up into 2. So dy dx is equal to, so the derivative of x is equal to 1 minus the derivative of e to the x is just e to the x. So that's the derivative. Now for what values of x is the curve stationary? So when is this thing stationary? So I hope we remember that stationary occurs when dy dx is equal to 0. So in other words, 0 is equal to 1 minus e to the x, or e to the x is equal to 1. So when is this equation here equal to 1? Well, the only time an exponential or a power equation is equal to 1 is when x is equal to 0. Okay, so there we go, we found the stationary point. So if we actually have a look at this function using our Desmos tool, here's x minus e to the x. I believe our function was x minus e to the x. You can see we've got this stationary point at 0, 1 here, where the curve comes up, slows down, stops, and then comes back down. So that is a maximum point there. So that's it for the first example, nice and easy. So just getting this idea back in to finding the stationary points. And example 2. So example 2 is a bit trickier. It's about normals and tangents. So let's just start with part A, and we'll get stuck into it. So this one says, let A be the point of the curve, y is equal to 4e to the x, where x is equal to 1. So what you're going to do is we're going to find the equation of the tangent to the curve at that point. We want to show that the tangent at A actually passes through the origin, which is actually quite easy. We want to find the equation of the normal at the point A. So we want to find the normal. We want to find the point B, so a second point where the normal crosses the x-axis. And then last, we want to find the area that those 3 points make. So let's have a look at part A. Find the equation of tangent to the curve at point A. So for a tangent, we need to be able to substitute some values into this equation here. So to do this, we need a point and a gradient, because this is the point gradient form of a line. So we've got an x value already, which is x is equal to 1, and we need a y value. So what we're going to do is we're going to substitute that back into the original equation. So y is equal to 4e to the x at x is equal to 1. So y is equal to 4e to the power of 1, which is just equal to 4e. So there's that y value. Now we're going to leave these values as exact values because it just makes life a lot easier. Okay, and it means we're going to get the exact value, not an estimation or approximation. So that's our y value. Now we need to find a gradient. So to find the gradient, we're going to do some calculus. So the derivative of 4e to the x is just 4e to the x, because remember the derivative of the x comes down, which is 1. So 4 times 1 is 4, and e to the x. So dy dx is equal to 4e to the x. Now at x is equal to 1, our gradient becomes, or our gradient is equal to 4e to 1, which is equal to 4e as well. So m is equal to 4e. So now we've got those 2 points, we can substitute them into this equation. Y minus y1 is equal to m lots of x minus x1. Okay, so we're going to substitute them into those values there. So let's start off with our y1. So our y1 was equal to, so y minus 4e, that's equal to 4e lots of x, and it's minus 1 at the x value of 1. Okay, so I'm going to expand the right hand side, and that's going to give us 4ex minus 4e, and you can see that we've got a minus 4e and a minus 4e on both sides, so we can cancel those ones out. And so that means our equation of the tangent is y is equal to 4ex, where the 4e, remember 4e is, e is just a value, so 4 lots of that times the x value, and so that's the gradient of our tangent, so that's the line of our tangent, that's the tangent itself. Now part C says find the equation of the normal at the point A. So for a normal, we need to start off with a gradient. So the tangent's gradient is equal to, well, that was equal to 4e. So the normal's gradient is equal to minus 1 on 4e. So it's a negative reciprocal. So what we can do now, we know what the point is. So at A, which is equal to 1, 4e, we can substitute y minus y1 is equal to m lots of x minus x1. So y minus 4e is equal to negative 1 on 4e, lots of x minus 1. Okay, what I'm going to do first is I'm going to multiply everything by 4e to remove that fraction, because that's really nasty. So this is going to leave us with 4ey minus 16e squared is equal to minus 1 lots of x minus 1. Rearranging that right hand side, that gives us 4ey minus 16e squared is equal to minus 1x plus 1. Okay, now moving everything to one side, so I'm going to leave this equation in its general form. We're going to get x plus 4ey minus 16e squared minus 1 is equal to 0. So what we might do now is we might have a quick look at Desmos and see what's happening with this curve and what's happening with this equation. So y is equal to 4e to the power of x, so this is our equation here. So we've decided that our tangent is going to be equal to y is equal to 4e to the x. 4ex, I should say. So here's our tangent in black, and I might just change this to projector mode just to make it a bit darker. And what you notice is that at the point approximately where our 1 value, and that's where it's going to line up there. And I actually might change it back for this one so we can see a bit clearer. So if I zoom all the way in at this point of intersection, you probably won't be able to see it, to be honest, but that's all right. We know that it's going to be our tangent points there. So that was our tangent. Now our normal, as we decided, was x plus 4ey minus 16e squared minus 1 is equal to 0. Have a look, here's our value of 1 here. And this is our normal that goes there. So it makes that perpendicular. So if I remove this one, it makes that perpendicular gradient, or has that perpendicular gradient. So it makes that 90 degrees with the other line there. Okay. So let's move on to the next question. So the next question says, part D, find the point B where the normal crosses the x-axis. So, that's part D, not part B. So we know that a line crosses the x-axis when y is equal to 0. Okay? Whoops. When y is equal to 0. Okay, so that's what we're looking for. We're looking for when y is equal to 0. And we're looking for at the normal. So in other words, what we're saying is we want when x plus 4ey minus 16e squared minus 1 is equal to 0, when y is equal to 0. So substituting that in, we get x plus 4e, lots of 0, minus 16e squared minus 1 is equal to 0. Well, that just cancels out that middle term here, okay? And that's going to leave us with x minus 16e squared minus 1 is equal to 0. And by adding 16e squared and 1 to both sides, I'm going to get x is equal to 16e squared plus 1. And there we go. So 16e squared plus 1. So if I go back to my picture and I look for when x is equal to 16e squared minus 1, and I'll give you a hint, it's going to be quite a whiles away, but if you have not minus 1, plus 1, and you'll see that's the exact point where it crosses this, this normal crosses the x-axis. Now our last question, we'll quickly duck back over to here, is to find when the area of our triangle AOB. So the triangle is the origin, this point here, and the line the tangent makes. So all this area underneath where the normal is, and the x-axis, so all this area here, up to this point, and then back down to this point here, okay? So what that looks like, or what that should roughly look like is, if I was to draw it, it's going to look something like a triangle like this, where this is 0, this is B, and this is A. And what I might do is I might actually put the values of these points next to it. So this one was 16e squared plus 1, and this one was 4e. 4e. Okay. So here's my triangle. Now, the area that I need to work out, well, we can see quite easily that this point here is 4e high, okay, and from this 0 point across to here, okay, this is 16e squared plus 1. So the area of the triangle AOB is equal to half the base times the height, so just the regular triangle formula. Now the height is at 4e from the 0 line up to the 4e, so it's a half times 4e, and then we're going to times that by 16e squared plus 1, okay, which is equal to 2e lots of 16e squared plus 1, and if you want to expand that out, it's going to give us 32e cubed plus 2e, and that's what the area is. So, a quite tricky problem, but something that we can 100% do. The only thing that's really different is that these e's are popping up. Now remember that e is just a number, and we can treat it just like a number, or you can treat it just like an algebraic letter. Okay, it doesn't really matter too much, because what we could then do is we could actually substitute the e back in, and we could say, not that one, so substitute e back in, so 32e cubed plus 2 lots of e. And we could say, well, it's actually equal to 648 units. And we know that's going to be roughly right because our triangle is quite big. It goes all the way up to 118, and it's almost, well, it's about 10 tall, so 10 times 119, and about half of that is equal to approximately 600. So, with that being said, that is the end of this video, and what we're going to do next is we're actually going to now look at the inverse of the exponential function, which is the logarithmic function. So I'll see you guys in the next video. Until then, I'll talk to you soon.